So if we graph the line y equals 2x minus 2 and we look at the line y equal x, then we can look at our possible inverse function, which is that g of x function. So x plus 2 over 2 is slope of 1/2, y-intercept of 1. And so that function is going to look something like this. And what we'll note is that those will end up being symmetric about the line y equals x. And you can verify this pretty quickly on Desmos. But again, we're not going to be using graphing very often just because it's so time consuming. Our main method of solving for inverses is going to be using the algebraic method. All right, so moving down here, we're going to look at some examples where we need to be careful about inverses being functions. And in particular, we're going to look at what are the conditions necessary for an inverse to itself be a function. So if I look at the quadratic function y equals x squared, we know what the general shape of that is going to look like. So if we were to reflect that about the line y equals x, or solve for it using the algebraic method, let's say, what we'll notice is that we're going to have an issue because when I square root both sides as my first step after switching the variables, the square root of x is going to equal plus or minus y, meaning that y is equal to rad x or y is equal to negative rad x. But obviously we can't be both of those things simultaneously because the square root of x will look like this. Negative 1 times the square root of x will be a reflection about the x-axis. And clearly this is not going to be a function by the vertical line test. So then the question is, well, how should we restrict this so that it does become a function? And so our standard way of defining this is going to be to shrink the domain of our original function, which means I need to get rid of one of these function rules. And so the one we will typically get rid of is the negative valued domains. So we're going to delete the negative square root of x, and we're going to let y equals rad x be our inverse function. So that means that we need to redefine our original function. So y is equal to x squared, where x is greater than or equal to 0. So that's going to be our restricted domain, which means that our new function is really just that positive half of the quadratic function. And then the inverse is going to be the square root of x. So f inverse of x is going to be rad x. And the quick way to identify graphically if you've got a function that's going to be needing to be restricted is what we call the horizontal line test. So if I draw a horizontal line through my function and it touches more than one point, that means that the inverse is not a function. And so that's going to mean that we need to restrict the domain. So we'll look at some examples below here. So we want to determine the domain of the original function and find the inverse function here. So our first function is pretty straightforward. It's a square root function. So we have radical 2x plus 3. We can note if we factored out the 2, we can figure out what the transformation is going to look like. So instead of our standard square root function starting at 0, 0, we'll note that 2x plus 3, that inside value of our domain, has to be non-negative, obviously. So 2x is going to be greater than or equal to negative 3, and x is going to be greater than or equal to negative 3/2 or negative 1.5. But transformationally, we can see we are shifted left 1.5 units and then vertically stretched. So we can vertically stretch the graph and then shift it. So what we'll end up with is at negative 3/2, we're going to get this taller square root function. And we'll note the domain of that function obviously is negative 3 over 2. So if we're finding the inverse function, we can do some work off to the side here. We'll swap x and y, and then we'll undo all of the operations. So we'll start by squaring and subtracting 3, it looks like. And so then we'll get that y is equal to negative 1/2, positive 1/2 times x squared minus 3. We could distribute that out if we want to as well. And what that is going to give us is a quadratic function. So 1/2 x squared minus 3/2, where our vertex is at negative 3/2. And because x is greater than that, y is going to have to be greater than that. So we'll note that y is going to be greater than or equal to negative 3/2 for the inverse function, because the domain and range switch. So that means we're going to get the positive half of that square root function. So no restriction necessary here, but we might want to notice how the domain and ranges switch for these functions. For number 2, now we've got another quadratic that we need to consider restricting. So its vertex is at negative 2, negative 1. And it's got 1/8, so it's vertically compressed, meaning it's going to be flattened or wider looking overall. But we can see here that with the quadratic function, our restriction is going to be pretty obvious. We want to restrict at the location of the vertex. We could pick the left-hand side of the graph, but I'm going to actually pick the right-hand side, similar to our original example. So we're going to restrict the domain so that it is from negative 2 to infinity. And now we're going to find the inverse function. So y is equal to 1/8 times x plus 2 squared minus 1. We'll swap our variables and then start the process. So it looks like we can add 1 and then multiply by 8. And then we can square root both sides. And because we have a domain of negative 2 to infinity, it'll be all the non-negative values of y plus 2. So we don't have to worry about plus or minus. I'm going to swap the order here. So y plus 2 is equal to the square root of 8 times x plus 1. And so then y is going to equal the square root of 8 times x plus 1. So that's going to be equal to our inverse function. And then finally, number 3, this function might not be obvious in what it should be. We will note the domain initially is going to be negative 4 to 4. We can see that if we want 16 minus x squared to be a non-negative number, it has to be larger than negative 4 or smaller than 4. But we're going to probably need to restrict that domain because the graph of this function is going to be something familiar. So we'll just note something to begin with is we can manipulate this. So we can square both sides and then add the x squared over. And what we'll see here is that this is the equation of a circle with radius 4 centered at the origin. So the actual graph of this function is going to be some portion of that circle. Obviously, it can't be the whole circle because that's not a function. So if we notice that the square root is always going to be greater than or equal to 0, what this gives us actually is the top half of the semicircle. So the square root function is going to be the top half of a semicircle centered at 0 with radius 4. But we can see here that's going to fail the horizontal line test. Right, so if I draw a horizontal line, it's going to touch 2 points. So again, now we have the option. We can restrict from 0 to 4 or from -4 to 0. And depending on which one you do, it's going to make your inverse kind of interesting. So for this example, I'm actually going to choose that negative domain. So in other words, I'm going to let the domain be -4 to 0. So we're going to get rid of this information here, and we're going to move that graph over so we've got a little bit more space. So we're going to take the quarter circle in the second quadrant here. Again, we could have taken the quarter circle in the first quadrant. So we've got y is equal to rad 16 minus x squared. We'll swap that domain and range, and let's see what we get. So we square both sides. So we got 16 minus y squared is equal to x squared. And then we end up with x squared plus y squared equals 16. So that's going to be the same equation that we started with. But what we'll notice is that our domain that we chose is the range of our inverse. So that means our inverse goes from -4 to 0. And we'll note that the range of our original function is still 0 to 4. And that will become the domain of our inverse. So that means x's are going to be between 0 and 4, and y's are going to be between -4 and 0. So what we're going to get for our inverse function is that quarter circle in the fourth quadrant. And that is going to be f inverse of x, but that's still just the square root of 16 minus x squared. So in other words, the semicircle's inverse is going to be itself the semicircle equation, just on a different domain. And if we chose that first quadrant, we would end up in the first quadrant. So that's kind of an interesting function because its inverse maps onto itself. So it would have the same domain and range values. So it has this sort of symmetry. Whereas if we chose this negative domain, we get opposite quadrants or diagonal quadrants from each other. All right, so the last part of the notes here is going to be on what we call even, odd, or neither symmetry. These are going to be pretty obvious from the pictures that we have up here. So even symmetry is symmetry about the y-axis. So we can see the graph is exactly the same if we were to slice it straight down through the y-axis. And odd symmetry, though, is a little bit different. So what we'll notice for neither symmetry, just being a parabola does not make you symmetric. So this is not symmetric. But for odd symmetry, we have a slightly different symmetry. But let's note that an even function is a function that is symmetric about the y-axis. So we call that an even function. We can't have x-axis symmetry for a function. So we'll look at x-axis symmetry with conic sections, but not with functions. But an odd function is a function that is symmetric about the origin. So if we are symmetric about the origin, you can think of that a couple different ways. Oops. So one would be rotational symmetry. So if we rotated our graph 180 degrees about the origin, so we rotate it all the way around, we would actually get the same graph. So it has 180 degree rotational symmetry. Another way to think about it is it has symmetry about x and y simultaneously. So if we reflected about x and y, we get the same graph. And then 3, the last one, is what we call point symmetry, which is if I constructed a line through that's going to pass through the origin, let's say, then the length on this side and the length on this side that are touching at those points are going to be congruent segments, meaning that any point on our curve is going to be equidistant from its opposite point. So we'll just note if this was at 1 on the right, so this would be 1, 1, then this point on the bottom here would be 1, -1. So that is one way of thinking about it as well, as that point symmetry. All right, so for both of these, if we have the graph, it's pretty easy to see the symmetry. So we'll note this is origin symmetry. But if it's shifted up, we can clearly see it's not going to have symmetry about the origin. So the question is, how do we verify if it's symmetric if we don't know what the function looks like, or if it's a much more complicated function? So the way that we're going to verify that is by looking at coordinates and how they correspond with that symmetry. So if I were to pick a arbitrary value, let's call it x, and I were to map that value of x, it would go to the coordinate x comma f of x, right? So wherever x is located. And if I were to take its exact opposite, so negative x, and I were to map it, it's going to map to negative x, f of negative x. And what we'll notice is those values are the same. So in other words, f of negative x, that y value on the left, is equal to f of x, that value on the right. So that is going to be our algebraic check. We're going to test f of negative x and show that it's equivalent to f of x. For odd symmetry, it's going to be the opposite. So we're going to pick a value, again, in the same way, so some arbitrary value of x, and we're going to pick its opposite. But what we'll notice is those points, oops, that is not the opposite. Those points are not going to map to the same values anymore. So we'll still have x f of x, or that's f of x, and then we'll have negative x comma f of negative x similarly, but now they're not the same, they're actually the opposite. So in other words, f of negative x is equal to negative f of x. So for example, if this was equal to 10, this would equal negative 10. So they will be the exact opposites of each other. And that is going to be our check, is to see if f of negative x is equal to the opposite of f of x. So again, those will be our two algebraic checks. We can kind of formalize it here in the notes. So if f of negative x equals f of x, f is even. Whereas if f of negative x equals negative f of x, f is odd. And then if neither, there is no symmetry. So if none of them work, then we have no symmetry at all. All right, so let's go ahead and take a look at the last four examples. You might pause the video here and try them on your own, but I'll go ahead and just start working into them. So again, you can pause it if you need to. So our check looks the same every time. We're going to change all of our x's to the opposite of x and see what happens. So we'll have negative x quantity squared plus 4 times negative x. So that's going to give us x squared minus 4x. So my first term is the same, but my second term changes. So we'll note that is not equal to f of x. That is also not equal to the opposite of f of x. right? Both signs would have to change for it to be the opposite. Thus, we have neither. So there is no symmetry in this case. For our second example, we'll do the same thing. So we'll have 3 times negative x to the 4th plus 2 times negative x squared. And here's where you can see why we use the term even. So even powers are going to make positive and negative numbers positive always. So we'll get 3x to the 4th plus 2x squared, which is equal to our original function. So this is an even function. For C, again, we're going to do the same check, but we'll just note we already know what this function looks like. So if it's a known function, you might picture the graph in your head and say, that is not symmetric about an axis or the origin. So this should not be. So if we have the square root of negative x, because it's an even root, right, root 2, we cannot take that negative x out. So it's just stuck there. So that will not equal our original function, and it will also not equal the opposite of our original function, which is negative rad x. So in other words, the negative cannot be taken out of an even square root. That would be different if it was, let's say, g of x equals the cube root of x. So the cube root of x, because we are allowing negative and positive numbers in its domain, this would be an odd function. And if you graph that function, of course, you'll see it's that reflected cubic graph. And so it will have origin symmetry. And you can check that with the algebraic rule as well. So finally for D, we'll check here. We'll notice all of our exponents are odd. So that's a good sign for a possible symmetry. And then we have 5 times negative x to the 5th minus 3 times negative x. So we'll get negative x to the 7th minus 5x to the 5th plus 3x. And then if we factor out a negative 1 from each term, we'll see that that is f of x. So we get negative f of x, and our function is odd. And let's note we are neither for the square root function. So that's going to be our typical check. What I'm going to do is add an additional example here that is maybe a little bit trickier. So let's add a little new note page here. So suppose we had f of x equals, and let's say we had, I don't know, x cubed over x to the 5th plus x cubed. Okay. And let's say this is x cubed, because we can factor this. Let's say plus 1. All right, so I've got odd roots everywhere, but I have this plus 1. So if I did f of negative x, I'd get negative x cubed plus 1, and then negative x to the 5th minus x cubed. So I could kind of play around with this expression. So I'd have negative x cubed plus 1. I can factor out a negative 1. So now my denominator is the same, and maybe distribute it in the numerator. And we can see here that it's still not going to be equal to either f of x or negative f of x. Because if I had negative f of x, that constant would be a plus. So there can be things that are almost odd or almost even that don't quite work out. So definitely be careful of that with the symmetries. And so that's going to complete the notes for our review chapter here. Couple of new things, couple of old things. So again, if you have questions, definitely let me know. And until I talk to you next time, take care.